Hi, so we're getting into chapter 4. We've made it all the way here, and we're talking about organic compounds. But we're not talking about the organic fruit that you buy at the grocery store. We're going to give you the scientific definition of organic compounds and what we're talking about. So we're starting to relate all of that hard chemistry to the biology. That's what this transition is going to be. You're going to see how chemistry applies to biology, and we're entering into the organic section of the course. All right. So we're going to start in these next couple of videos. We're going to talk about the structure of organic compounds, and we're going to talk about the simplest compounds before we get a little more complicated. And you're going to probably need to make some flashcards for section 4.3. All right, so organic compounds. All right, the scientific definition of organic compounds. All right, they are composed of carbon. You're always going to have carbon and hydrogen. All right, carbon and hydrogen, that's going to be there. But in some of these families that I talked about for section 4.3, you're going to see that it's going to often include oxygen also, nitrogen, sulfur, phosphorus. All right, very important, amongst a few of the other elements. All right, ones that you've seen before and that you recognize. All right. So as I said, you're going to see how this applies. So some of the biomolecules that you've heard of before, like proteins, all right, proteins, like an antibody is a type of protein, all right, everyone's heard of those. Carbohydrates, all right, lipids, so fats, DNA, I don't know why it's broken up this way on this slide, but those are all organic compounds, all right, organic, all right, biomolecules, life. Okay, so that's what we mean by organic in chemistry class. So we've already seen that there are some different ways that you can write out the structural formulas for compounds. And we're going to expand on this a little bit more. So we have condensed structural formulas, which are going to show all of the atoms in a molecule, but as few bonds as possible. All right. And they may or may not show lone pairs, all right? So sometimes you're going to have to really think about your Lewis dots and what electrons are really there in your valence shell, all right? So we're going to have this condensed structure here, all right? So you can see that that condensed structure is just a little bit more broken down than the molecular formula. So the condensed structure, it's telling you a little bit more, right? Just sort of plainly written out, you know, how many hydrogens are attached to this carbon and so on and so forth. It's just a little bit more broken down, whereas here, you just have your molecular formula that shows you the number of each atom in the molecule. Like we just know total, that there are 3 carbons and there are 8 hydrogens, all right? But this is the same thing, all right? It's the same compound right here. See, you have 1, 2, 3 carbons and 6, 7, 8 hydrogens. All right, but it's just broken down a little more. You can see where those bonds should be. And here in this Lewis structure, the bonds are drawn out. All right, so that is your full Lewis structure, all the way broken down. Those bonds are there. So you're going to have to make sure you understand the differences, because you're going to have to apply it between the molecular formula, the condensed structure, and the full broken down Lewis structure. All right. All right. So, and not only that, we have our molecular condensed Lewis, and we're going to have another type of structure called the skeletal structure, or bare bones. All right. See right here. Can you see kind of why they're called bare bones? All right. You're not going to have the carbon atoms written out there. All right. And you're not going to have the hydrogen atoms written out there. All right. So those are the bare bone structures. All right. Bonds to other atoms that are not hydrogen, those are going to be shown. And I'll show you an example of that on the next slide. I'll draw something out for you guys. But what you can see here is this represents a carbon on this line, This represents a carbon and this represents another carbon. But you just don't write the C. And you know that it's assumed that there are going to be hydrogen there. And see, there is no hydrogen that is drawn right here, is there? So this is the bare bones structure, all right? And this is a ball and stick model. So this gives you a three-dimensional picture of what that compound would look like in reality, okay? So there are some rules to follow for drawing these skeletal structures. And whenever you're studying, you can write these out before you start to draw any of your structures, all right? So first, the bonds to carbon are shown. So carbon is first, bonds to carbon, all right? Then the bonds between carbon and hydrogen, so those aren't going to be shown, but they're implied, all right? Like I said, they're assumed. But other elements that are bonded to carbon are drawn at the end of the bond using their chemical symbol, all right? So really, you're going to have these skeletal bare bone structures drawn only when a compound is going to have more than 3 carbons, all right? So 1, 2, 3, all right? You don't have it for just 2 or for just 1, all right? And you're going to have other elements that are bonded to carbon that are going to be drawn using their symbol. So for example, if we have 1, 2, 3, oops. No, it's not what I wanted to draw. So if we have 1, 2, 3, and let's say that this carbon is bound to an oxygen, and let's say that oxygen is bound to a hydrogen. So, all right, if these atoms have hydrogens bonded to them, these hydrogens are shown. You see what I just did there? You're going to see that this is like an alcohol group, all right, this OH. So you are going to draw out a hydrogen that's bound to another element that's bound to carbon, all right? So we're going to do plenty of examples and you're going to get used to that. So the lone pairs, all right, so you know that if you have some lone pairs there, those are not going to be shown. So if you draw it out where you know that oxygen has 6 valence electrons, all right, 5, 6, and you see that one of these is bound, all right? But let's say in some instance where you would have a lone pair that you might need to draw there, all right? The lone pairs are not going to be shown, all right? But just think about your valence electrons, all right? So representing the structures of organic compounds is basically everything that we're trying to do here. So there are more rules here for drawing the skeletal structures, just sort of some simpler or more simple directions rather that you can follow. So first, draw the number of carbons connected end to end. So start with carbon. So start with carbon. Then you're going to draw the bonds between the carbons. Draw the bonds between the carbons. So first, just write out the symbols. Just draw them all next to each other. Then draw the bonds to carbon. And then you're going to draw the bonds to the non-carbons, all right? Then you're going to draw the bonds to the non-carbons, like you see right there. All right, so those are some rules. If you're saying, oh, I don't know where to start, well, that's how you're going to do it. Okay. So let's do some problems so that we can see some examples. All right, so here we go. 4.1. Describe the difference between a Lewis structure and a condensed structure in terms of atoms and bonds shown in the structures. All right, this is a good one to start with. So what's the difference? Let's make a little table. That helps if on the study guide that you make for yourself, you make a little table. So we have our Lewis structures, our condensed, and we have molecular. And they're just asking us about Lewis and condensed. All right, see how I underline my goal right there? So, all right, in terms of atoms and bonds. So in Lewis structures, you have everything, right? You're going to have all of those atoms. They're all there, all right? And you're going to have all of the bonds. It's all written out. You just have everything. In condensed, you're going to have the atoms there. The atoms are going to be there. All right. We're not talking about bare bones, right? We're talking about condensed. So you have all of the, you have the atoms. You have the difference here as few bonds as possible. All right. So that's a big difference there. And similar to the bare bones, you usually don't show the lone pairs. All right, we're going to draw some condensed structures. Okay, so 4.3. Explain why it is not possible to draw a skeletal structure for methane. Well, I just answered that one just now, right? So we've looked at methane a couple of times, right? Methane, if we're going to draw the molecular formula, this is methane, a carbon that's bound to 4 hydrogens, because you know carbon can make four bonds, because that's how many valence electrons they have. So why can't you draw out the skeletal structure? So here is the molecular. All right. Let's see, here is the condensed. It's just like this. That's it. There's no other way you can condense it even more. You have your total carbon, your total hydrogen right there. All right. Then what about skeletal? And we've drawn out the total Lewis structures before for methane. Well, why can't we do a skeletal structure? Because why? I just said that there has to be 3 carbons. How many do we have? 1. We only have 1. So there's only 1 carbon. And you need 3 carbons, to draw a skeletal structure. Skeletal structure. All right, that's just the way it is, because you're not going to have anything that's less than that. All right. So, okay, breezing through, just a breeze. 4.5, draw a skeletal structure for each of the following compounds. All right, I'm definitely going to do A. All right, so we're going to draw a skeletal structure here. So let's see, how are we going to do this? I like to count these carbons, and that helps me to keep track. So let's see. 1, 2, 3, 4, 5. And we have a 6 carbon here. Okay. So how are we going to write this? So we're drawing a skeletal structure. We're not going to write our C's, are we? We're not going to write our C's. We're going to start like this with dots, but we're not going to have this in our final product, but this is just to keep track of carbons. I like to draw it out this way. So 1, 2, 3, 4, 5. That's 5. 1, 2, 3, 4, 5. All right. And on the second carbon, you see the second carbon is bound to a hydrogen here, a hydrogen here, or a couple of hydrogens here, and another carbon. This carbon is bound to another carbon, which is bound to 3 hydrogens, right? So you're not going to include these dots in your answer. You're just going to draw 1, 2, 3, 4, 5, 6. And that's how you draw that. All right, so that is the answer for A. All right, so I guess I can go ahead and do B. So how are we going to do this? We know that we have 1, 2, 3, 4 carbons, and one of those bonds between carbon is double bond. Okay, so we have 1, 2, 3, 4, and on that last one we have a double bond. So we're just going to draw a double bond like that. And we're not going to write the hydrogens. See, we don't write those in there. So these are not included. They're assumed. Not included written-wise, but they're assumed. Carbon and hydrogen are such good friends, they've got to be there together, right? Okay, so that is the answer for B. All right, so let's move on to, we're doing that one in class. 4.7, draw a Lewis structure for each of the following compounds. All right, A. We're going to write a Lewis structure for this. So we know that we've got 1, 2, 3, 4, 5 carbons. So let's just go ahead and write them out. 1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. And you see that, so let's go ahead and draw our bonds. So we wrote out our carbons. Now we're going to draw our bonds. We see that we have a double bond between these two carbons. All right. Then we have a single bond, and a single bond between these carbons. All right. And then we see on the fourth carbon, we are bound to a chlorine, and that's what our lone pairs are going to look like on the Lewis structure, right? For chlorine. All right. So if we were to draw it out that way, that's what we would have. So that's basically what you would have. And so you can also include your hydrogens. So you would have 3 hydrogens bound to this carbon, right? And this carbon is going to have, it's going to be bound to another hydrogen here. This one is going to be bound to 2 hydrogens. This carbon is going to be bound to 1 hydrogen. It's also bound to carbon here and another carbon on the other side. And you're going to have this carbon, it's bound to this carbon. So it's going to have, it's got double bonds. That's getting messy. There you go. So it's going to be written out this way. So you have to keep track of how many bonds carbon can make, all right? So that being said, I know y'all want practice problems, so I'll leave B for y'all, and y'all can see the answer in the book. So you go work on B and make sure that you can do that. All right. Okay. Let's do 4.8. Draw a Lewis structure for each of the following compounds. All right, so 4A, let's draw a Lewis structure. All right, 4.8. So how are we going to do this? No, my bad. This is the one that we're going to work in class. All right, let's move out to 4.9. All right, let's do 4.9. It wants us to draw the condensed structure for the following compounds. So for A, it wants us to draw the condensed structure. Okay, so how are we going to go about this? First, let's count our carbons. So we have 1, 2, 3, 4, 5. We have this 6th one here. So let's see. We're going to write out our carbons. So 1, 2, 3, 4, 5. All right. So we know that this carbon is bound to this alcohol group. So we can go ahead and write that in. All right. And so we can just draw our bonds first. We can draw it out this way. We know that all of these carbons are going to be bound. And we know that on this 3rd carbon, we're going to be bound to another carbon. All right, so now we can go through and take out these bonds because we're going to know what's going to come right there, right? What's going to come here? Well, this carbon is bound to 1 carbon, but it needs to bind to 3 other things, right? It's going to be 3 other hydrogens. All right, so what you're going to write is CH3. All right, and then you're going to have this C that's going to be bound to the alcohol group. All right, and it's going to be bound, so it's bound to oxygen. So let me make that a little more clear. It's bound to the oxygen, all right? And if it helps you to understand what to write, you can draw out the entire Lewis structure if you want. So if you know that you have carbon that's going to be bound to 3 hydrogens here, and you have 1 carbon that's bound to 2 carbons, bound to an oxygen, what is this carbon going to be bound to right here? It's going to be bound to 1 hydrogen. All right, so you can write it out however it makes you comfortable. So you're going to have that CH3 on the end, then this carbon is going to be bound to a hydrogen. All right, and so we can write that a little more neatly. You have this carbon that's bound to 2 carbons. So what else is it going to be bound to? So this carbon is bound to this carbon is bound to this carbon. So you're going to have bonds to 2 hydrogens. All right. Because you already have 1 bond right here. All right. And you're going to be bound to that other carbon. Remember, you're going to be bound to another carbon. So you're going to just have CH2. All right. Because you're bound to these carbons in the carbon chain. So you're just going to have CH2 right there. And this carbon is going to be bound to hydrogen. And this carbon is going to be bound to what? If it helps you out, draw the entire Lewis structure before you start. All right, so you have 1, 2, 3, 4, 5. All right. You have all right. And you're going to have this carbon is bound to 2 hydrogens, and this carbon bound to 3 hydrogens. So, all right, so you have these last 2 carbons. So you have 1, 2, 3, 4, and that's going to be CH2, see here, and then CH3. All right, so sometimes it helps to go ahead and draw out your Lewis structure so that can help you write your condensed structure. All right, so it shows as few bonds as possible, but you can see where we did draw the bonds. All right, and so you're going to go ahead and erase any of those stray markings. All right. All right, so let's move on to, all right, 4.2. So we are looking at the simplest type of organic compound, and that's an alkane. So we're going to be talking about alkanes, alkenes, and alkynes. And so you're going to have alkanes and then alkenes and alkynes. And so alphabetical order, A, E, then Y. They're going to gain complexity by going in alphabetical order. So you could think of it that way, just an easier way to remember it. So if you have an alkane, all right, so here we have A, that is the simplest type of organic compound. All right, And the reason that they are simple is because they contain only a single bonded carbon and hydrogen. All right, that's it. Just a single bonded carbon and hydrogen. And typically this is referred to as a saturated hydrocarbon. So that those carbons are saturated with hydrocarbons. So let me draw sort of an example. So if you have this compound, all right, where you have as many hydrogen bonds as you can, because you only have single bonds to carbon, single bonded carbon and hydrogen, you're going to be saturated. So this is saturated with hydrogens. Saturated with hydrogens. And on the other hand, you're going to see what it looks like when something is unsaturated. All right. So you're going to see that whenever the bonds between carbons change. All right. So a hydrocarbon indicates that alkanes are made up entirely of hydrogen and carbon. Hydrocarbon, hydrogen and carbon, right? It makes sense. So saturated, single bonds. All right. You're only going to have single bonds. When you start having double bonds, the saturation decreases. It's not so saturated, and it's going to be referred to as unsaturated. Okay, so each carbon atom, in addition to being bonded to the other carbon atoms, is going to be bound to the maximal number of hydrogens. So if it's not the maximal number of hydrogens that carbon can be bound to, then it's not saturated. All right, it's unsaturated. So straight chain alkanes are going to be made of carbon atoms that are connected to each other. It's going to make a continuous sort of line structure. All right, it's a chain, exactly what the name states. It's a straight chain alkane, and it's going to be unbranching chains of varying length. So we're going to see where you can have an alkane that has 12 carbons in their chain or 22 carbons in their chain, and that's going to have more biological implications. All right, you're going to see what I'm talking about. So each carbon is given a name, all right, based on the number of carbons in that chain, based on its length. That's how we're going to be naming them. And so the names of the first four alkanes, all right, are used today, and they're really easy to remember. And I'm going to show you that in the next couple of slides, and I'll give you a little mnemonic that's kind of silly to help you remember. The names of the alkanes with 5 or more atoms are going to be using Greek prefixes, okay, followed by ane, A-N-E. So you're still going to have that, so you can realize that they're talking about the saturated structures with the single bonds, ane, the simplest. All right, so you can write an alkane general formula like this: CnH2n plus 2. All right, so the number of hydrogens is not just going to be double the number of carbons. It's going to be doubled and then plus 2. Okay, because if it's just doubled, that's something else, and we're going to talk about what that something else is. So here are the prefixes, as I promised, in a table. All right, so we're talking about types of alkanes, and so there are the 4 main ones in the list, or ones with the number of carbons between 1 and 4. So if you have 1 carbon, the prefix is meth, and I told you the ane is still there, that's methane. Or 2, ethane. C, prop, that's propane. 4, butane. All right, so M, E, P, B. And so you can think, this sounds so silly, Me eat peanut butter. All right. That's just a silly way to remember it. Okay, but it's an easy way to remember the prefixes for alkanes. Me eat peanut butter. There you go. So methane, ethane, propane, and butane. All right. Methane, ethane, propane, butane. All right. And after that, you have those Greek prefixes that you're already a little bit familiar with, right? So I told you that for an alkane, we would have a formula that was like this for the number of atoms. But for cycloalkanes, it's going to be a little bit different, right? So whenever something is a cycloalkane, you're going to see how that contrasts to the formula for just an alkane. So cycloalkane, you think of a cyclo like a sickle, bicycle, cycloalkane, all right? So this is just, it's like a silly little drawing of a bicycle, but can you kind of understand? It's a ring structure. All right, they are ring form alkanes. All right, so single bonds. So however you need to remember cycloalkane. It's like a ring structure. All right. So all you do, the names of cycloalkanes are, you know, they're just made by putting the prefix cyclo on the alkane name for a compound containing the same number of carbons. So the simplest cycloalkane, so like you have alkane, that's just going to be the one carbon. So you have propane. All right. So that would be cyclopropane. You just add cyclo to the front of it. All right. So that's going to be the simplest cycloalkane. And if you're going to have rings that have 5 or 6 carbons, those are going to be the most common in nature. And we're going to see some examples of those. All right. As promised. So here you have the skeletal structure for cyclopropane. All right. And here, so you see, all right. So when you have the number of carbon atoms, all right, you have methane, ethane, propane, butane. All right, remember those. All right. So here, all right, you're going to have cyclopropane. All right, here you're going to have cyclobutane, cyclopentane, cyclohexane. All right. So what's going on here as far as the formula goes for a cycloalkane, you're going to have your carbon, your number of carbons, and your number of hydrogens is going to be twice the number of the number of carbon atoms. See, like 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10, 6 times 2 is 12. So knowing the differences in the number of atoms between the carbon and the hydrogen, you can tell if it's an alkane or a cycloalkane. All right. Okay. And so you understand that to make a ring structure, you've got to have those 3 carbons there. So you're going to have the simplest one, cyclopropane, and you're going to have cyclopentane. It's going to have 5 carbons, and cyclohexane, that's going to be the most popular. These 2 are the most popular in nature. Okay, so those are popular. All right, so those alkanes, you have to understand that they are going to be nonpolar. Okay, so when you're thinking of polarity, you have to remember the electronegativity. And we said that the electronegativities between carbon and hydrogen are very close. So we're going to consider that to be covalent, and that's nonpolar. You're not going to have that partial positive and partial negative charge. All right, so that's, you're having something that is mostly carbon and hydrogen. All right, so regardless of the shape, the alkanes are going to be nonpolar. All right, so try and remember that. All right, and that's because you need to understand the polarity of these structures because it has a role or it affects the functionality of those compounds. Okay, so know that the alkanes, write it out for yourself. Alkanes, nonpolar, no matter what. Okay. All right. So alkanes. So you can think of alkanes as your fuel sources, right? So that's something that is going to combust. All right. So alkanes are going to react with oxygen and combust. So you're adding alkanes to your car when you go fuel up at the gas station. You can think of it that way. When hydrocarbons are combusted, you're going to end up with carbon dioxide and water. All right. So just understand what this means so that basically you can understand the functionality of that type of compound, an alkane. All right. And so you know that all the time scientists are looking for cleaner and cheaper hydrocarbon fuels. All right. In an effort to get rid of fossil fuels. All right. Or supplant them with something else. Okay. So, and if you are interested in that topic and you want to know more about other fuel sources, we can talk about that. Just let me know and I can find good articles for you guys to look at. So, the simplest organic compounds are going to be the alkanes, all right? And just remember that. And they're simple. Why? Because of those single bonds. Everything that you see here has a single bond. So you have methane, that's just one carbon. Propane, you got 3. All right. Isooctane, all right. Those, you have some different structures. So you might want to remember these, but you're probably not going to have to memorize these this way just yet. All right. So these are just some examples of some alkanes. So if you think of propane gas, if you like to use propane burners, all right, this is what you're using. All right. We looked at that formula earlier, one of the first slides. Hexadecane. All right. So diesel. All right. Isooctane. That's when we're talking about putting alkanes in your car. So alkanes are a big deal. All right, just understand we use alkanes all the time. They're something quite tangible, nothing abstract about it. All right. So, all right, we're going to get into families as our last section for the video, but let's work some of these problems. All right. So in the problems, you have your tables for here. This is for naming alkanes. So it's the first 10 alkanes, and that goes by how many carbons there are in the structure. All right. Okay. And here are the cycloalkanes. And their structure names, their ball and stick models, their molecular formulas, skeletal structures. All right. So that being said, we can work a few of these problems. All right. So 4.11, name the straight chain alkanes and cycloalkanes whose structure or formula is shown. So we want to name the straight chain alkane or cycloalkane. All right, A. So, all right, we already know they're alkanes because it tells us that in the problem, or cycloalkanes. All right, not going to be anything else but that so far. So what do we have? Well, we can count our carbons. 1, 2, 3, 4, 5. All right. We have 5 carbons. And if we draw this out, we'll see that this is just a straight chain alkane, right? So, but how can we do that? Well, let's see. If we have how many carbons? C5. And how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is the number of hydrogen atoms only double the carbon? No, it's not. It's double plus 2. So this is going to be an alkane. It's not cyclo. and it's 5, so that's what? 5 carbons? That's pentane. All right. B. We have 6 carbon, 12 hydrogen. Oh, well, the number of hydrogens is double that of what we have for carbon. So that's going to be a cycloalkane, and we have 6 carbons. So that's going to be cyclohex for 6. Ane, our simplest single bonded alkane, ane, A-N-E. All right, cyclohexane. So C, 1, 2, 3, 4, 5, 6, 7. 7, and it already shows us this is not a cyclic structure. So this is just going to be heptane. All right, and it's just as easy as that, y'all. All right, so now we are going to write the condensed structure for the straight chain alkanes. A, heptane. All right, so I'm going to show you a trick, and I will do the first and the second ones for you, and then you can do the third one. You can do C. All right, so A, heptane. So we know this is an alkane. It's not cyclic. It's just going to be the line structure. So we are going to have, so no rings, and we're going to know that we have 7 carbons. 1, 2, 3, 4, 5, 6, 7. 7 carbons. All right, and those carbons are going to be bound to hydrogen. So a carbon on an end can be bound to 3 hydrogen. And what about the others? They're just bound to another carbon on each side. So silly. 1, 2, 3, 4, 5, 6, 7. All right, so here, that carbon is going to be bound to only 2 hydrogens. This carbon, the same. They're going to be the same all the way, and you can write out your Lewis structure so that you understand. And on the end, this carbon is only bound to one other carbon, so it's going to be bound to 3 hydrogen because it can make 4 bonds. All right, so methane, you've seen methane before. What do we need to do with it? Nothing. That's it. It's everything that a condensed structure needs to be, right? All right. So you can do decane because it's going to be a lot like A, right? It's going to be almost just like A, except there's going to be more in the middle. And you can check your book and see if you got it right. Use the same formula that I did. All right. So write the skeletal structure for alkane or cycloalkane shown. All right, A. So we have 6 and 12. All right, so we know that this is cyclohexane. Cyclohexane, because this is double, exactly double the number of carbons and hydrogen atoms. All right, so we have, if we're going to make a cyclic structure, 1, 2, 3, 4, 5, 6. Yep. So that's how you're going to draw that, except you're not going to write the little numbers all around it. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There you go. All right, B, butane. All right, so we know that that's 4 carbons. All right, and we have 1, 2, 3, 4 carbons. Let's write it out in our molecular formula. So we have, if we're writing our molecular formula, so here we have our condensed, and our molecular formula is going to be C. All right, 1, 2, 3, 4, and H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's just ane. So that's butane. 1, 2, 3, 4. That's it. That's the answer. All right, for B. So now C, you can do C. All you have to do is count 1, 2, 3, 4, 5, 6, 7, 8. You know there's going to be 8. You know there's going to be 8 already. Is it cyclic? You got to see if the number of hydrogens is just double the number of carbons. And if it's not, that's going to be ane. It's going to be an alkane. All right. So is it an alkane? You tell me. Work it out and check it in the book. All right. Okay, now let's go through 4.3. All right. So section 4.3. Let's see. All right. Families. All right. So these compounds are important because they do things. All right. So they're going to have functions. All right. They're going to function. They're going to do something. So that's exciting. Things are happening. So elements other than carbon and hydrogen, I told you, all right, they're going to be present in these compounds. And we're going to talk about which ones again. You might remember from the earlier sections, but those other elements are going to be called heteroatoms. Heteroatoms. All right. Heteroatoms. So the atoms are going to be bound in a certain way that makes it a functional group. Okay, so organic compounds are organized into these families, and the families are going to work in a similar way. That's what their commonality is. They're going to have a similar function. All right, so the functional group is going to have certain properties and reactivities, all right, that it has in common with other groups in its family, okay? Other functional groups in its family. So it tells us about the behavior. So that's why it's important to know these. And you're going to have to know these functional groups. So you're going to want to maybe make a Quizlet or write it out. You're going to have to find, use a mnemonic device, some way to remember it. All right. So some people think that that's difficult. Some people think it's fun. I don't know. I think it's based on your perspective. All right. So, all right. So some of the functional groups, all right, like we learned about alkanes, and we're going to learn about alkenes and alkynes and aromatics. All right. They are hydrocarbons. So they're going to have hydrogen and carbon. Remember that, right? Okay. So a lot of the functional families are going to include heteroatoms, right? Those are atoms besides hydrogen and carbon. And those often will be oxygen, nitrogen, and sulfur, right? So a lot of times there's going to be a carbon double bonded to an oxygen. So there's going to be something like this. And you're going to call this a carbonyl group. I know that doesn't sounds like it'd be carbonyl, but it's not. It's carbonyl, all right? And so that type of group is going to be found in several families, all right? So get familiar with that because you're going to see it a lot, all right? So the functional group is the reactive part of the molecule, all right? That makes sense, right? Function means acting. It means an action. So the functional group is the reactive part of the organic molecule. So if we're going to keep looking at just the functional group, that's going to be attached to the rest of a molecule, rest of a compound. We're going to just refer to the rest of that molecule as R for rest, creative, right? So R just allows us to simplify the structure so that we can focus on the functional group, all right? The part that works, all right? The part that we care about right now. So that R might be from 1 carbon to a whole chain of 22 carbons, all right? So I know it's a lot. So there's going to be a lot of, note card making, I think, because you're just going to have to remember a lot of these. So you're going to have some of these organic compound families of function groups, and they're going to be listed in this PowerPoint for you and in your book. So You know, whatever you don't have on your best friend, you're going to have to be able to recognize. Like, you're not going to be able to have to write these, but you need to be able to recognize. Okay. So alkane. So you just have to recognize an alkane. All right. So we know that that's a saturated hydrocarbon. You can put as many hydrogens as you can around that molecule. All right. And then we're going to talk about alkenes, which are unsaturated hydrocarbons. All right. So they're going to have carbons that are double bound to each other. They're going to have this really strong bond between each other, but they can bind less hydrogens then because they're bound to each other. All right. They have a double bond. So there's only so many other bonds they can make. It's not as many hydrogen bonds that they can make because they're already bound to another carbon. All right. They're double bound. So that's an unsaturated hydrocarbon because there are still hydrogens in carbon. So it's hydrocarbon. And alkyne, so if you have a triple bond, that's even less hydrogen that can be bound by the carbon. So that's very unsaturated hydrocarbon. So that's alkyne. So you see alkane, ene, ine, A-E-Y, single, double, triple. All right. So it's sort of an alphabetical order from simple to more complex. Okay, if you want to think of it that way. So we're going to have aromatics. All right, so we're going to talk about those, and those are ring structures, and they're named that way because of sort of this aroma that a lot of them give off. All right. Alcohol, you're going to see that a lot. That's this OH group that you see here. All right. A phenol, so that's going to be this ring structure that's attached to an alcohol. All right. And you're going to have an ether group. So you're going to have an oxygen that's going to have these R groups on either side. Okay. So that's like Benadryl, like you see here. And whereas a phenol, an example of that would be like estradiol. All right. That's a female sex hormone. Okay. So, all right. Sorry, I had to plug in my device. Okay. All right. So, and you can see vitamin B3. All right. So that's an aromatic structure. And when you're looking at triglycerides, so you see 3, 1, 2, 3. This is your alkanes, alkynes, alkenes, those types of things. So you have your alkanes here, you have your alkenes here. So these are not abstract things. They're very important in a biological setting. All right, that's the point here. So if it helps you to understand what these things are in reality, then go ahead and make sure you understand those things. And you're going to need to know those things, you know, now and for your future classes. So I would recommend very much making some flashcards for this, because, you know, you can make mnemonic devices. If you want me to try to come up with a mnemonic device for more of these, I can help you with that. Something that each of you can remember. But really you need to sit down and think about these things, right? And if you started looking at the chapter already, you know this is coming, okay? So you're going to have these other groups, all right? So whenever you're going to have this sulfur here, all right, bound to hydrogen and bound to an R group, you're going to have something called a thiol, all right? So you're going to have a thiol. And then whenever you have a sulfur that's bound to an R group on either side, you're going to have a sulfide. You're going to have a sulfide, all right? And then you can have a disulfide, and that is 2 sulfurs, all right? So you can have that too. So here's an example in a compound where you have a thiol group, a thiol or thiol group, or here you have a sulfide right here, and you see it's bound to those carbons on either side, all right? So it's got some R groups on either side. So that would be a sulfide, all right? And a thiol right here. And then you have a phosphate. Phosphate is so important, right? Without phosphate, we don't have energy because phosphate is needed for ATP. You need phosphate. So look at these phosphate groups that are in this whole ATP structure, all right? And y'all have heard about ATP before, I think, right? Adenosine triphosphate, all right? So that is so important. That's what we need to do anything, all right? That's our energy exchange. That's the body's currency, ATP. So that's what a phosphate looks like. So you see, and you have R, it's attached to the rest of the molecule, all right? The rest of this biologically important structure. All right. And then you're going to have amines, all right? So you can have primary amines, all right? So like here for the stimulant amphetamine, all right, you can have a primary amine where it's going to have one R group and it's going to be like bound to these two hydrogens. Then you can have a secondary amine where you can have an N group that is going to be bound to two R groups and a hydrogen, or a tertiary where the nitrogen is going to be bound to three R groups, three rests. And like you can see that, or they don't have an example right here, but they do have one for a quaternary amine where you have nitrogen that's bound to four groups, four R's. So like you can see here, it's bound, nitrogen is bound to these four carbons, all right? So you have, and then you also have protonated amines, all right? So you can have all of these different structures as well. So start getting yourself familiar with this, okay? So you can also have an acetyl group, right? And that's where you're gonna have an R group like you have here in this acetyl coenzyme A. That's very important biological enzyme, okay? So you're gonna have this acetyl group where you're going to, so these are the carbonyls, all right? Oh, I didn't even mention before. Well, no, we're good. All right. So here, all right, so you're going to have carbonyl groups where you're going to have carbon bound to oxygen, all right? And inside of here, you're going to have acetyl groups, all right? So you can see where you have oxygen double bound to carbon, all right? And here you have, you're bound to another carbon and you're bound to the rest of this molecule here. You have an R group, and you're going to have an aldehyde where you're going to have basically like your carbonyl, but you're going to be bound to a hydrogen here in your R group. Or you can have a ketone where you're going to have your like carbonyl, but bound to two R groups, all right? So you can see that, all right, an aldehyde right here. And you can see here where you have a ketone group where this carbon and the carbonyl is going to be bound to two other carbons. All right. And you can have carboxylic acid. All right. Where you have your carbonyl that is going to be bound to this alcohol. So you sort of have two functional groups right there. And that makes carboxylic acid. All right. And carboxylate. All right. So start getting familiar with these. I know it's a lot, and we still have a few more. I know it's so many. Hopefully this gets you to want to really get in there and learn some of these. So here you have an ester where you have this structure again, this carbonyl, all right? And you can be bound to an oxygen that's then bound to the rest of the compound, and you can have an amide, all right? So you're going to have an amide where you have the carbonyl bound to a nitrogen right there, amide, ide. So that's different than an amine, right? Okay. So we talked about alkenes. And so we talked about alkanes, but we haven't exactly talked about alkenes, just briefly. So we have unsaturated hydrocarbons. So before we had saturated hydrocarbons, we had as many hydrogens as we could around those carbons. It was saturated with hydrogen, but now we have unsaturated hydrocarbons because we're going to have double bonds between our carbons here. All right, so that's going to be an alkene. So you're going to have the carbon-carbon double bond. All right, so there aren't as many hydrogens that can then bind around those carbons, right? So they have more than one bond between the two carbons. So they're going to have a really short and strong bond between those electrons. All right, a very strong bond between those carbons that are in the alkene with the double bond. All right, so in an addition reaction, all right, the second bond of that double bond is going to be broken, and the carbon atoms are going to be joined together by a single bond. So these are very, very strong bonds. And alkenes are going to be more reactive than alkanes, but not as reactive as alkynes. And we'll see that on the next slide, I think, or in the next few slides, rather. So here you're going to have an alkene. And so here's an example. So ethene. All right, so the ethene, we were kind of talking about things that are secreted from fruit that aid in the ripening of other fruits. So that's the ethene doing that there. All right, so they are found in terpenes. So they contain one carbon-carbon double bond and multiples of 5 carbons. All right. And so some of the terpenes would be like beta carotene. So these really, really important molecules, beta carotene, right? You need that. But also needed from terpenes would be cholesterol, right? You can't survive without cholesterol. All right. Testosterone, estrogen. All right. So really important hormones that are going to be made from terpenes. All right. So you need alkenes. They're a big deal. All right. Not just something abstract, right? Okay. All right. So for our unsaturated hydrocarbons that are alkynes, you know that you're going to have a triple bond between your carbons. All right. So triple bonds. So those are in the alkyne family. So they are unsaturated, even less hydrogens bound to this type of compound. So it's even stronger than the alkenes bond. Whenever you have the triple bond, those electrons are really highly bound to each other. All right, they're very attracted. So alkynes are more reactive than alkenes, as I stated before, and they are pretty rare in nature. So like if you think, all right, like different toxins, all right, so they are rare in nature, but they are very important and they are very interesting. All right, so we can get some gain a lot of knowledge from alkynes as well. All right, so we have more unsaturated hydrocarbons, and those are going to be aromatics. All right, so that's whenever we're going to have this ring-like structure. So they are sort of they're sort of based on this benzene type of structure. So this family of compounds has this sort of volatile aromatic nature. All right, so it is aromatic, named for pleasant aromas. So like everything that you're smelling in Bath and Body Works, right? Like aromas, so aromatics. So they have a cyclic structure, all right? So like the ring structure. And so whenever you're going to have a lot of rings or they're part of a really large molecule compound, they are going to be referred to as phenyl. So the carbon-carbon bonds of benzene are all going to be the same length. And these bonds are also going to be really strong, really stable, and very strong. So benzene can withstand things that other double bonds that are not in a ring structure could withstand. So that's because of something that happens called resonance. So you're going to have in these unsaturated cyclic aromatic compounds a lot of stability. So the electrons that are forming these double bonds here, they are free, all right, to move around, all right, to move around the carbons that are there among the 6 carbons. So this results in something called a resonance hybrid. So something called resonance happens. And so basically, like this bond right here can move. And then that sets off a chain reaction, and this bond can move within this ring structure. And this bond can move within this ring structure. So basically, so this is resonance. So basically, you can draw this structure, and that equals sort of what's happening right here because those electrons are so free and they can move. And so those are some very stable bonds between those carbons and those double bonds in the hydrocarbons that are aromatic. So if you have 2 or more of those benzene rings, all right, that's poly, they're cyclic, and they're aromatic compounds. So those are PAHs. You've probably heard of those. Or you'll see some products now that say, no PAHs or whatever you see advertised, things like that. Because a lot of them are environmentally or clinically unfriendly. So polycyclic aromatic compounds. All right, so 2 or more benzene rings. All right, so you're hearing, all the benzene rings are bad. You're hearing these things a lot more often now. So you're going to find some of them in tobacco smoke, which we know is not good. Some are found to be carcinogenic, and some are useful and they're used in plastics. All right, so it just depends on how you use them. All right, some good, some bad. So we're going to be using a lot of these molecules, right? They're included in organic compounds that are pharmaceuticals, medications that you take. So whenever you have that medicine that you purchase and you look at that little flap of paper that gives you all sorts of details about the medicine, you're going to see the structure of the medicine, because the structure gives you some information about the function, right? It's not the first time you've heard those 2 things connected, right? Structure and function. So here you have some pharmaceuticals that are known as opioids, all right? Morphine and oxycodone. You have these powerful opioids. That's how these structures are grouped together right here. Another pain medication, tramadol. So we have found that the structure of a compound makes its function similar, so that even if something does not have the same structure, even if it looks like the other structures, it can have a similar function. So you might know this naloxone, you might have heard of it as Narcan. So whenever somebody is having a problem with some of these opioids, something like Narcan is similar that can be used, that can prevent, it can be used in a similar way, but can sort of compete with and replace the negative effects that some of these opioids that can give you if you take too much of them, right? So Narcan is used on people who may be overdosing on morphine or oxycodone, all right? So you can use something with a similar structure that might have a similar function in a way that is desirable, all right? So some of those hydrocarbons are really important. They are lipids, all right? So fatty acids, all right? So those are really important to our health, all right? We need lipids. We need lipids. They make up our cells, right? So fatty acids belong to the class of biomolecules that we call lipids, all right? So if they have one double bond, just one double bond, that's mono unsaturated. It's unsaturated because it can make less bonds with hydrogen, right? If it has a double bond. If it only has one, it's mono unsaturated. All right, so mono unsaturated, if you must have fats that are unsaturated, mono would be better. Okay, better for conception. So those with two or more double bonds are polyunsaturated fats. So saturated fats are long, straight chain alkanes, just single bonds, alkanes. All right, so just the single bonds like this. All right, they do not have double bonds and they have a carboxylic acid group. All right, so we saw that with the carbonyl and the alcohol. All right, so it has that at one end. All right, so the most biologically important fatty acids are going to usually have 12 to 22 carbon atoms, and a lot of times an even number of carbon atoms at that. Okay, so, all right, so here are some examples. Don't really have to memorize these or anything, but really, so you see the structure of a fatty acid that comes from coconut and from nutmeg, from palm, peanut, and canola oil. And actually, canola oil is really, I can find a table to show you guys in class, but canola oil is actually a pretty good oil for you to take. Or to eat or to cook with, actually, if you're looking at the fat content. Whereas there's been a big movement towards coconut oil. But the benefits of that compared to canola oil haven't necessarily been shown. So you kind of have to follow the literature with that. All right. So the FDA recommends that you have a maximum of 30% of calories in a normal diet coming from fatty acid containing compounds. So it's recommended that the majority of the fat be, all right, so majority of our fat intake come from foods containing mono and polyunsaturated fats, all right? So mono and polyunsaturated fats, all right, as opposed to saturated fats, all right? So, with that being said, you do need fat in your diet, right? It's important for sort of this insulation role in covering your neurons, right? So you need that to to sort of protect your nervous system and other internal organs. So fats are very important. Without that, you could not function. So this is opposed to saturated fats. All right. Oh, yes. So the data is included here. As you can see, with the coconut oil, you have all of this saturated fat, whereas canola oil is mostly polyunsaturated and monounsaturated. So canola oil is actually pretty good to use. All right. Even though a lot of people are using this coconut oil, but the coconut oil has a greater percent by weight of total fatty acids that are saturated relative to mono and polyunsaturated, right? So you got to follow the literature on that. All right, so we're not going to go to 4.4. We're just going to work a few more problems here. All right, right here. All right, so let's go. Let's do 4.17, I think. You're going to do that? Yes. Okay. So identify the family of the hydrocarbon present in each of the following. I know it's intimidating, but it's really not. And we're going to do problems in class too. So if you have a triple bond, what do you have? You're not going to have alkane. You're not going to have alkene, but you're going to have alkyne, right? Because you have that triple bond. All right. B. All right. Now you've got some double bonds here. You've got double bonds. All right, so it's unsaturated, and that is an alkene because of that double bond right there. All right, so you have this alkene chain of hydrocarbons. All right, so, all right, you can go ahead and figure C and look in your book to see if you can get the answer for that one. All right, so let's do 4.19. All right, so benzocaine. All right, put this in your mouth when you have an ulcer so that you can have sort of a numbing sensation instead of feeling that pain. All right, so let's see what we've got here. We've got to identify all of the functional groups. So that's probably more than one, right? And you can see here, you've definitely got more than one. So let's see, what do we have here? What groups do we have here? All right, so I think we have what? What group do we have over here? All right, where we have this oxygen, all right, bound to carbon and oxygen. Do you remember this? You have, what are you going to call this group? That's an ester. All right, so then what are you going to have? You're going to have another group, all right here. All right, where you're going to have an N that's bound to 2 hydrogens and another group that's going to be called a primary amine. Think of nitrogen, N, amine. All right. Or if you know to think of like amino acids, all right. So, but I think we're going to get into that later. All right. So what else are you going to have? All right. So be able to name these structures. All right. So, all right. So you know you've got plenty of functional groups there. So let's see what you've got here. All right, something allyl mercaptan found in chives. All right. So what have you got here? What's this? That's an alkene. All right. So all right, what have we got here? We've got this S and we've got this H. All right, so we have this SH. So you remember, look back or where the sulfurs were on that table. Where were the sulfurs? And what did that say? All right. So what do we have here? This kind of group. And then that's bound to the rest. What do you have here? You have something called a thiol group. So really all it takes is for you to go back and start looking up some of these to make sure that you understand what they look like. All right. So let's do 4.21. All right. The most prevalent fatty acid in coconut oil is lauric acid, a saturated fatty acid containing 12 carbons. Draw lauric acid in skeletal structure. All right. So fatty acid. So what are going to be the main components in the fatty acid? We're going to have an alkene, all right, or alkane, and alkane chain, and a carboxylic acid. All right, so we're going to have 12 carbons. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so basically, if you draw it without the dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and at 12, this carbon, we're going to have a carboxylic acid, right? So we've got our carbonyl group. We've got this alcohol. We've got our 12 carbons. Should be right. All right, y'all. So I think we're going to go over the rest of them in class, spare you some time on this video, and start looking at all of those families and functional groups and making note cards. All right, thank you.